All right, thank you. So I have the honor of being the first talk of today, so I'd like to do acknowledgement of country. So we would like to pay our respect to the First Nation Australian members of our community by acknowledging the traditional owners of the land on which I am located, the Whadjuk people of the Noongar Nation. Yeah, so today I want to give a whirlwind update on what's been going on in the world of gas cap H1. And so I'm doing this on behalf of the entire GasCap H1 collaboration, and I am currently here in Perth. I am a Bolton Fellow at CSIRO. So GasCap is the Galactic Gas Cap Survey, and its aim is really to understand galaxy evolution better by studying the gas in the Magellanic Clouds and the Milky Way. You can see where my bias is there in describing that. And it's really going to be an impactful survey. Here you have in the grayscale image of current existing H1 all sky image, and you see where the gas cap survey will cover, which includes the low latitude with deeper integration, intermediate galactic latitude, and then the entire Magellanic system. And so this survey will be more sensitive than any of the previous H1 21 centimeter surveys by about an order of magnitude. So wrapped up, ASCAP has wrapped up the phase 1 of the pilots of each of the key science projects. And so for GasCap, for our pilot phase 1, we decided to do 3 different fields. And the first was looking at the galactic plane at a longitude of 340 degrees. We wanted to try and tackle the galactic center, which would arguably be the most challenging region to image, and so we could test the technical capabilities. And then also to cover the small Magellanic Cloud and the first part of the extension of the stream and the bridge. And so far, it's a really difficult task to image all of this data. And so we've imaged all of the small Magellanic Cloud region. And so that's largely what I'll be showing you today. And we've also are just in the process, well, Nick Pingle, our project scientist, is in the process of imaging the galactic plane and the galactic center, although the data quality there is a little bit not as great as in the SMC fields because of some technical issues in the data at the time. So I've shown this a number of times, but I realized when I showed this to a collaboration group on Friday that when I don't give the context of what the observations looked like before, it's not quite as impressive to see the current observations that I'm presenting. So this is the previous best observations of the small Magellanic Cloud taken with the compact array and Parkes. And so here is a T-peak image, and then we can switch over to now the SMC observations from pilot phase 1. And so this is a T-peak image that Nick Pingle had imaged using CASA. So we had developed an imaging pipeline that used CASA and multi-scale clean. But now we've been experimenting with WS clean, and it's doing a much better job. So it might be a little hard to see the details, but you can see that it's just doing a better job, I think, at recovering the structures on all of the size scales. And this is combined with the Parkes data as well. And really is just giving us a much better quality image because it takes into account the primary beam from the holography of ASCAP. And so now for the first time, we have good enough quality data that I will present to you a moment zero map of H1 in the small Magellanic Cloud. And this is nothing fancy here. This is literally me just integrating over the entire velocity range that we've imaged. So that's it's about 100 kilometers a second. And so this is the version done with WS Clean. And so to give you the full idea of what the velocity structure in the field and just the detail of observation that we're able to get with this data, here's just a nice little video of the small Magellanic Cloud progressing through velocity space. And you can really see that we're resolving for the first time these really small scale features, a lot of filamentary structure, and then these anomalous velocity structures, higher velocity structures outside the main body of the SMC, which of course Naomi had presented in the Nature Astronomy paper a couple of years ago based on the test data. And so, of course, at the same time as we get these observations towards the Magellanic Clouds, we're also getting the Milky Way velocities in the foreground. And so this is actually the cube of the Milky Way velocities in the foreground to that SMC field. And this is particularly exciting for being able to trace like these high latitude, high velocity clouds. And you can just see a great amount of detail and some really interesting filamentary structure, which is a lot of people in the collaboration are working on. So there's a lot of science that will be able to be done with just this pilot data, but then it really gives us a bright future for where we'll be able to go with the gas cap survey. And so like part of pilot phase 1 is starting to build up towards what gas cap will look like as a full survey, right? We did these 3 different fields that are connected and on the grid that we hope to image on. And so here is the previous gas survey, the single dish observations of this region. And now here was what it looks like when you piece together only 3 ASCAP fields of view. So now you're able to see really the detail of the small Magellanic Cloud and all of the gas that's kind of streaming out from it in the bridge. It's going off towards the large Magellanic Cloud and the stream that's flowing off towards the north. And so these are really structures that we've never seen before at all. So we'll be able to look at the neutral atomic media and its connection to the galaxy evolution of these 2 clouds, and then also begin to look at how this gas may be interacting with the Milky Way halo and how that can inform us about the evolution of our own galaxy. So we have a number of working groups, and so I just wanted to highlight what those are and what the current results are happening from each of those. So first is H1 absorption. This is being led by James Dempsey, who is part-time as a PhD student at ANU with Naomi McClure-Douglas, and also at CSIRO working on CASDA. So it's really nice, understands the technical details of uploading the data and understanding how that works. He will be giving a talk next, so I will tell you very little except to say that we are also doing H1 absorption in all of these fields, and it's very, very exciting. John Dickey will be talking on Friday about some work that he's been doing using the absorption towards this galactic field and the really exciting, really strong detection of H1 absorption towards the outer galaxies. So we're talking 25 kiloparsecs away and further, which is really presenting us with a unique view. And again, these are just giving us tastes of what will come with the full survey, and we're setting up how we will deal with the analysis of a much greater volume of data. Another active area of research is spectral decomposition. So this is both in the emission, which is being shown here, as well as in the absorption. And so previously, particularly for the absorption, any kind of Gaussian decomposition was mainly done by eye. And of course, we don't find that particularly reliable. And as we start to get to the quantity of absorption spectra that we'll have with gas cap, we really won't be able to do that. There will just be way too many sources to look for absorption and to be able to understand the different velocity components in each of those spectra. And then on top of that, you can also use this on the emission to try and decompose the different velocity components as well as the different width components and try and assign those to the cold neutral medium, the warm neutral medium, or an intermediate phase. And so a lot of work is being done. Claire Murray is leading this working group, but also a lot of work is being done by Antoine Marchal. And so we're initially using Gauss, Pi, and Rosa. And I think the real catch here is how do we quantify the uncertainty in this, because there's a lot of degeneracy in being able to put in little small Gaussians to add up to a larger spectral feature versus a wider Gaussian, and how do we really know how well we're able to do that with the data. Nick Pengel, who is the H1 project scientist for GasCap, is leading the working group on turbulence. And so he's just finishing up a paper right now, which will be the presentation of the pilot data the pilot phase 1 data for the Small Magellanic Cloud. And his real interest is in the turbulence. And so he's been looking a lot at the spatial power spectrum. And so here, excuse me, I'm showing you the spatial power spectrum from the ASCAP data. So from our pilot survey data in the blue. And so then there's a power law fit, which is slightly shallower than the previous data from the compact array. And so what that's suggesting is that perhaps at higher resolution, we're seeing the smaller scale feature, and there's actually more power on those smaller scales than what we're able to see before. And then finally, the fourth working group is on filaments. Of course, we now know that the ISM generally has a lot of filaments everywhere. And so the idea is how can we pull out that information in an automated way in these large-scale H1 images. So this is being led by Susan Clark at Princeton, but a lot of work is initially being done by Jackie Ma, who's a postdoc who started with Naomi, but is still in Germany. He will be giving a talk on Thursday, so look forward to that. And so what he's been doing is using the rolling Hopf transform to identify filamentary features in the H1 emission across the entire field. And so I just want to quickly throw up that some of the work that I've been doing with Jackie, so a little bit of interplay between both the, new groundbreaking observations from ASCAP and also from other observatories. So in my case, that's ALMA. And so I've shown this before, but I'm working on finally writing it up. This is my large scale map of a small region-ish, smallish region of the southwest bar of the SMC. And what I've been looking at are this idea that maybe there are these long filaments in molecular gas. And my question with Jackie is, do these line up with H1? And so here, the gray contours on top of an integrated intensity map of the H1 on the same velocity range as the CO filament, which I've highlighted in blue. And you see that the filaments, or generally the bright H1 emission, is offset from the CO, but the CO does sort of tend to follow it. So there's promising information here, but this is really just being started, and we'll progress more. So for phase 2, what do we have coming up? Oh, I guess I did not shift that one. We will be covering this entire field. So we really recognize that the strength at the moment with our processing capabilities is to really just image large areas and just see what's out there. So we'll be doing the entire Magellanic field, not the entire Magellanic, but the main portion of the brightest emission, connecting both the small and the large Magellanic Cloud, as well as a test observation with Wallaby to see if ZUMO2 in the galactic plane, the intermediate latitudes, will be good enough to accomplish both of our science cases. And so just give you a taste of what's coming for the large Magellanic Cloud. I know a lot of people are interested in this. This is the previous ADCA observation, so just the interferometer only at 60 arc seconds. And here are some test observations where the data quality is not good. We're not using this for science, but does give you an idea of what it looks like at higher spatial resolution. And I was in a collaboration meeting for 30 Doradus, and so here's just a comparison to give you on the small scale features that we're really being able to see the small clumps. And as we test out our ability to image at 10 arc second resolution, we have a promising future. And so I will leave it there.
Okay, thanks, Katie. Unfortunately, we don't have time for questions, but if you have questions, please put them in the Slack channel for the session, and we can get to them there. So yeah, so next, I guess we should stop sharing. So if James can share his screen at this point. Okay, great. James, I think you.
Yep.
Yep. Okay. No, he's sharing it. Yep.
Does anyone know the keyboard shortcuts?
Yep, swap displays probably is going to help you.
Yeah, that's good.
There we go.
Sorry about that. My name is James Dempsey. I'm a part-time PhD student here at ANU, and I'm going to be talking today about the absorption work that we've been doing within the gas cap group. So just to start off a little bit of orientation. First, we have here's the Magellanic system in neutral hydrogen emission. And this is showing the Magellanic stream and the two clouds. Now, because this is emission, this will be mostly warm gas, which is between sort of 5,000 to 8,000 Kelvin. But there will be cold gas there as well. And so, particularly within the clouds, we know there's cold gas. There's also cold gas within the stream as well, a matter of finding it. That's between 20 to 200. And there's also going to be gas in that intermediate range as well, between 200 to 5,000. Now, our aim here is to map this out. So this is an image from the gas survey done single dish, so at Parkes. And our aim is to get the absorption data to the point where it can be mapped out in a similar way to that. And I'll show how we're going along that way. And the importance of that is then we can see the distribution of the gas, and we can see how get an idea on its formation. And that helps because it's important because the gas is all part of the this sort of the food cycle of galaxies. And as the gas cools down, it condenses, becomes denser, and eventually becomes molecular, and then into the star forming region. So let's have a look at what we knew about the small magnetic cloud up as a couple of years ago. This is the compact array survey, Jameson et al. 2019. And we've got around 37 detections. Those are the orange circles. And we have out of 55 total background sources. And you can see it's very focused on the body of the galaxy. And it is, but not much exploration of the wider field. This is the view from KAP. And so here we're seeing, we've got an even view across the entire field. We're exploring for the first time those diffuse regions around the galaxy. We can see we've got around 7 times as many sources, almost twice as many detections. From this image, it's fairly obvious the detections are clustered around the denser parts of the galaxy. That's expected. But there are also some outliers, some places where there is absorption in the diffuse areas, and also in front and behind the galaxy itself. I should also note that this is 20 hours observing, as Katie mentioned. Back to the previous one was 100 hours observing to observe every target. So KAP is going to be an amazing instrument for absorption science. So a typical spectrum. So here we're looking at the top is an absorption spectrum. The black line is the amount of light which is let through from a background continuum source. The red line is the continuum level. The first thing that's obvious here is that our spectrum, when there's no absorption, is sticking quite nicely to that flat line. It's a nice flat bandpass, which is fantastic. There's also relatively low noise, and that means that when we get absorption, we can measure that quite accurately. And here we can see we've got 3 absorption detections, one quite deep, one very shallow, and one fairly wide. At the bottom there is the emission spectrum from the cube that Katie showed just earlier. And it's interesting interesting and probably expected that the absorption is aligned with those peaks in the density of the warm gas. Just one thing to note as we go on to the next slide here, in an absorption scale, 1 is all light gets through, 0 is no light gets through. So the lower the e to the minus tau, the more absorption is happening. So let's do the fly through of the SMC. Here we're seeing a green outline is a 2 by 10 to the 23 per centimetre square column density limit. It's just an arbitrary boundary for the SMC. The grey background is the emission from the emission cube from KAP. And the circles are where we see absorption. Now, you see as we run through here that the absorption is again very, most commonly where there is emission, and that's again expected. But we do have these outliers, we just had one then, which are away either from the cloud or in front or behind. Now, some of those we know are probably excess noise, but the majority of them are actually they're real absorption in diffuse areas, which is intriguing and exciting. So with a rich and unbiased coverage, we can look at the properties of the cold gas in bulk. And so here we're looking at a Coulomb distribution function of all of our spectra split into those we detected absorption, those we didn't. And so the first, and also excluding some of the high noise ones where we wouldn't be able to get a detection. So the first thing here is that over on the right-hand side, within the boundary of within the density limit of the SMC, that's where most of our detections are, and that's expected. But we do see some on the left in the more diffuse areas. Also interesting is what we don't see here, which is that this isn't a step function where all of the absorption is in the every sight line from a particular density onwards has absorption, and none earlier on. So it's much more nuanced than that, in contrast to perhaps what some previous authors have put forward. So let's check on the spectra themselves. And this is an example of one of those ones in a diffuse area. But the first thing I'll call out is just comparing the gas KAP spectrum with the compact array spectrum. We can see there's the same structure, there's the same velocity range. It's quite reassuring that we're getting good quality spectrum, we can trust them. The other interesting thing about this particular one, if you look down on the bottom left, is we're seeing self-absorption from this this particular feature is because it's in such a strong absorption in an area where it has low emission. The second comparison highlights why ASCAP is again such a brilliant instrument for absorption. On the right, you've got the compact array spectrum. The source was a bit off the beam center, therefore the noise is high. You can see there's absorption, but you can't reanalyze it. There's too much noise there. On the left, we can see the gas KAP spectrum because every source is going to be within 1 or perhaps even 3 beam centers. There is a much more even coverage across the field, and we're getting much lower noise spectrum. So in this particular case, beautiful low noise spectrum, really complex absorption, lots of overlapping cold clouds, lots to work with there. So just to wrap up, I'm going to touch on the Milky Way. Now, John Dickey will talk a lot more about this on Friday, but in this field, we've because it's closer and it's denser, we're seeing a lot more absorption. There's coal gas everywhere. So we get a lovely coverage of the galactic plane, which is diagonal on this plot, and also above and below. So 82% of the sight lines have absorption. That's without even accounting for those that have noise. So with such a great coverage, we can then go ahead and do some of the mapping I talked about earlier. And this is a longitude velocity diagram. So effectively looking down on top of a slice of through a cube at the galactic plane. The negative velocities are the inner galaxy, the positive velocities are outer galaxy, out beyond the solar circle. Now obviously, the area there is darker because it's harder, it's further away and harder to detect. But there's a couple of features I wanted to call out here. The first is that along the bottom here, you can see there's a lovely terminal velocity line, which are very clearly called out in the coal gas. And also there are channels within the inner galaxy where there is, they're effectively empty. There's a lot less coal gas there. And that reflects probably the action of the bar and the structure of spiral arms. And just to wrap up, we can then compare that against an earlier survey, in this case, a Southern Galactic Plane survey. And we can see the same structure is called out here. Between the two lines there on the right is the same velocity range that we're looking at in the absorption. And we can see the same features there, really nice correlation, really well picked out. That's all, thank you.
Thanks, James, for that really great talk. So it looks like Elaine has a question in the Slack. She asks, very interesting to see lines with H1 column densities as high as 10 to the 22 centimeters per squared. Can you say anything about the likely spin temperatures of this gas?
We haven't delved into the spin temperatures of the gases yet. It's on the next on my to-do list. But it's we're getting some high tau values, so we do expect there'll be some fairly cold gas in that area, but we haven't really got an idea of the spin temperature just yet.
Okay, great. So it looks like there is a question that's being typed, but maybe, oh, there we go. Emma Ryan Weber asks, are all the continuum sources background of the SMC Milky Way or some within?
So within the Milky Way, certainly there is a proportion of sources which are within the sort of in the near fields or within the galaxy itself. The same will happen for the SMC as well. So we expect there'll be a mixture of sources, and that also may affect the absorption we get, because if you have a source which is within the galaxy, it obviously won't absorb any emission which is behind it. So that will also affect what we see in absorption. It's an important distinction.
Okay, great. So it looks like there aren't any more questions right now, but if you have any, please put them in the Slack and James can get to them later. Let's all thank James again for his talk. And then next we have Ruby Wright, who will be talking to us about exploring the buildup of gas in simulated galaxies.
Is this the microphone?
Yeah.
Yeah.
You have to share it.
Okay, great. How is that microphone working online? Just want to make sure everyone can hear. All good? Okay. Yeah, so thanks, Christine. My name is Ruby Wright, and I am a final year PhD student at ICRA in UWA. And as part of my PhD, I've been doing a lot of work with the EAGLE cosmological simulations. And today I want to talk a little bit about some of the work we've been doing trying to measure net gas accretion and comparing centrals and satellites. But to start off with, I kind of want to talk about, I guess, a wholesome overview about how observations and simulations are really working together to come to a precise understanding of the baryon cycle in galaxies. So on the left, I got a lovely illustration from Freke van der Voort, which is illustrating all of the different gas flows which define the baryon cycle. And on the right, I've done my best to sort of collapse this down into one dimension. And I think it's fair to say that, I guess, it's the balance of inflows, outflows, and star formation, which really defines how a galaxy will evolve over time. Now, what I kind of really want to highlight here is that down here at the, I assume you guys can all see the mouse, yep. Down here at the galaxy end, we can really, I guess, use observations to, I guess, constrain, I guess, the stellar mass, the gas mass, and star formation rates of galaxies. But as we move a little bit further up the ladder here towards the accretion side, it's a lot more difficult, and there are multiple reasons for this. So for instance, the gas that is accreting is typically about 100,000 times less dense than the ISM of galaxies themselves. And gas on first infall to a halo, when it's in free fall, you don't necessarily expect it to exhibit a strong kinematic signature, unlike the energetic feedback-driven outflows that we can observe. Even despite these difficulties, there have been some incredible studies with small samples looking at detecting gas inflow, but then of course, basically detecting gas inflow and statistically quantifying it are two quite different questions. And I think this is where cosmological simulations really come into their own, because we can use their predictive power while working within the constraints that we do have down at the galaxy end to really explore the gas flows in detail. So with that little spiel for simulations, I want to talk about satellite galaxies. Now, I think we're all familiar with the idea that a satellite's environment has quite an influence on its star formation status. So this is the famous plot from Peng's 2010 paper, where you can see that for a fixed stellar mass, a satellite galaxy or a galaxy in a more dense environment is more likely to be red or quenched. And there are basically the idea of this work is that we want to explore using gas flows, directly measuring gas flows in cosmological simulations, why this might be the case. Now, a lot of previous work with cosmological simulations have focused, well, explicitly measuring gas flows have really focused on central galaxies. So we want to make sure that the satellite galaxies also feel included. So in this context, the processes or the terms stripping and starvation or strangulation are thrown around quite a bit. Stripping refers to essentially removing of star-forming gas, the removal of star-forming gas, whereas starvation or strangulation refers to the lack of gas inflow. And these are two different processes, and studies often try to pin down the mechanism for quenching to either one or the other. But the reality is that both of these processes, in all likelihood, are happening at the same time. And in fact, simulations have shown that satellite galaxies, even in the most extreme of environments, will to some extent be accumulating new gas. But it's the balance between this gas inflow and the outflow which sets how that galaxy will evolve and whether it's actually quenched. So the question for this work that we pose is a bit different to previous work, and that is, under what circumstances can galaxies actually net grow their gas reservoir? And sort of a question that comes under that is, can satellite galaxies still net accumulate gas in a group environment? And then seeing if we can sort of pin down when stripping versus starvation and strangulation might be dominating in different circumstances. Now, as I alluded to, we're using the Eagle cosmological simulations for this work, and I won't talk too much about the simulation itself, but I will talk about how we are measuring inflows and outflow rates. So this is a picture of a 10 to the 12 solar mass halo in Eagle. And I think if I gave all of you the task of delineating between the CGM and the ISM in this picture, we'd all probably come up with different answers. So it's important to sort of define what you mean by the galaxy. Previous simulation-based work has often defined, I guess, an arbitrary sphere at 15% of the virial radius of the host halo, and then took all of the cool gas within that envelope to define the ISM. But of course, in our circumstance where we want to be measuring this as satellite galaxies as well, using the host R200 value is not appropriate. It's not physically linked to the size of the satellite in many cases. So to make sure our method was agnostic to the status of a galaxy as a satellite or central, we used Adam Stevens' method to measure the baryonic radius of a halo, of a galaxy. And to do this, basically we define a natural endpoint for the galaxy where the cumulative mass distribution becomes essentially isothermal. And then, so this is, the middle panel sort of shows what that Barry MP sphere looks like. That's the term we use. And then to define the ISM, you essentially just take all of the cool gas within that envelope. So to define cool, we use a temperature cutoff of 5 times 10 to the 4 Kelvin. And that's what it ends up looking like there on the right. Okay, so what I'm showing you here is the stellar mass of galaxies, and then as a function of stellar mass, the fraction of galaxies in each mass bin where the inflow rate actually exceeds the outflow rate. And what I'm showing you is the centrals in blue and the satellites in the redder colors split into 3 bins of halo mass. I think it's fairly obvious to see that at the lower mass end for satellites in more group type scenarios, you can see that they're very seldom sort of accreting, right? So there's about 10% of galaxies in this mass range that might be able to still be net accumulating gas. It's not zero, but it's not very common either. Now, if you move to sort of the more dwarf size halos where you might be expecting to find satellites in a more pair type situation with their central, you can see that satellites are actually perhaps even more likely to be growing than their central galaxy, which is an interesting result. Now, if I reduce this sort of parameter space in a window of stellar mass and take the ratio of the stellar mass of a galaxy to its host halo, you can see that satellites obviously span a much larger dynamic range in this parameter space, but you can see that there's a very tight relation where you can see essentially that satellites with a lower mass relative to their host halo are much less likely to be net accumulating gas to their ISM. If you move up to more intermediate stellar to halo mass values here, you can see that in the small overlap in this parameter that centrals and satellites do have, they actually behave very similarly. So about 60% of galaxies in this mass range can be, or in this range of stellar to halo mass ratio, can be accreting. And this sort of has quite important implications for semi-analytic models, which normally assume that galaxies are, satellite galaxies are cut off from cosmological accretion as soon as they are part of a group. And interestingly, the centrals actually show the opposite trend, where if a satellite, a central is larger in relation to its halo, it's less likely to be net accreting gas. So you can see that only about 20% or 20 to 30% of centrals with
a higher stellar to halo mass ratio will be accreting. And these are the centrals that sort of have, that we'd be expecting to have to be in a more field type environment. So they don't have a lot of galaxies surrounding them, and they might be in perhaps a void of the cosmic web. And I won't speak too much to this other than to say that I'm definitely excited to look into this a bit more in the future. So this is all at a very statistical level, but I sort of want to take you through what this looks like for a satellite at sort of on the left-hand side of this parameter space here. So what I'm showing you here is the infill of a 10 to the 10 solar mass in stellar mass satellite into a 10 to the 13 roughly solar mass halo. Now, with the help of Rhys Polton, who is an ex-UWA PhD student, he has developed Orb Weaver, which is a program that essentially generates an orbital catalogue for cosmological simulations. So this allowed us to identify all of these different infill events. But what you're seeing here on the left is the trajectory of the satellite. In the middle panel is a sort of zoom in on the satellite, and on the right there are a few panels showing the orbital radius, the inflow and outflow rates, the stellar mass and cool gas reservoirs, and the star formation rate. And I think, as you can see, before the satellite enters R200, the inflow rate exceeds the outflow rate and the galaxy is still net accreting. But as the satellite enters R200 and passes through its pericenter, the outflow rate definitely exceeds the inflow rate, and you can see this cool gas reservoir starts to decline. Decline quite drastically. And this is sort of reflected in the Barry MP envelope that you can see here. So before entering R200, the envelope is quite large, and as this cool gas envelope is sort of stripped, you can see that the baryonic radius sort of shrinks just to encompass the denser stellar core. And interestingly, a result that we found is that as the satellite passes through its pericenter and then outside the R200 into its apicenter, you might expect that the inflow rates could pick up again, right, as the galaxy is less under the influence of the halo. But this isn't what we see, and in fact, even when the outflow rates drop to 0, the inflow rates at apicenter again do not pick up. So we're sort of seeing this stripping and then starvation type scenario. Now, with the orbital catalogues that we were able to generate with Rhys's Orb Weaver, we can sort of take this back up to a statistical level. And what I'm plotting here is the fraction of satellite galaxies growing before first infall or at their first R200 crossing in black. And then in orange, I'm showing the fraction of galaxies growing at their pericenter. Now, unsurprisingly, that fraction drops quite dramatically, particularly for the lower mass satellite galaxies. And that sort of feature that we saw before, that at apocenter, the satellite galaxies weren't able to then start accreting again, we actually see statistically as well. So at the apocenter, the satellite galaxies, if they survive their pericenter, are even less likely to be net accreting. So this is quite interesting. And there are a number of different mechanisms that we could talk about, and I haven't exactly pinned down what this could be, but obviously the satellite galaxies are net losing mass for a while, and they may be sort of inducing less gravitational attraction to the surrounding gas, or it could be that the gas is more likely to favor infall to the host halo rather than the satellite itself. So again, we're seeing the stripping and then starvation sort of type scenario on a statistical level. So I've got my conclusion slides up here, just sort of split up into the different mass ranges. So we see very low growth fractions for low mass satellites in larger groups. And these growth fractions actually continue to decrease along the orbit of a satellite. And that we see this stripping and starvation scenario. Now, the high mass satellites in group environments and the centrals in group environments, we see that they have quite similar accretion behavior, which again has applications to semi-analytic models. And then, as I mentioned, the centrals in the field, more field type environments seem to really not be accreting too much at all. Now, future work in this sort of line of what I've been doing is going to focus on the mechanisms as to why we're seeing the stripping and then starvation scenario, and how we can actually sort of link this to observations. So a lot of observations might suggest that there you would expect a different metallicity sort of evolution if you have a stripping versus starvation type scenario, and we can measure that in simulations as well. And as I alluded to, I'd be very interested to look at the influence of a centrals environment on their net growth. And is the fact that centrals in the field environment are much less likely to be growing, is this entirely environmental, or is there also perhaps an influence of feedback happening? So with that, I will say if you do have any ideas or specific use cases for this work, please do get in touch, and I'm happy to take questions.
Okay, thanks, Ruby. So yeah, there's several questions here in the Slack channel. First, Anshu asks, very interesting results. Can you please talk a bit more about why centrals across 3 orders of stellar mass have similar net growth rate?
It's a very good question. And while that net growth rate, it's not necessarily, I was plotting the fraction of galaxies that were net growing. This doesn't necessarily reflect that net growth rate, yeah, which does vary quite a bit over that stellar mass range.
Okay, the next one's from Luca. He asks, what physical processes dominate the inflow? Are these filaments, merging, or more simply condensation of gas from the CGM?
Yep, so there's a combination really of cosmological sort of pristine inflow, which is about 50%, and then at least it's z equals 0, and then there's recycling happening as well. And those two, there's sort of a redshift evolution there, definitely, but mergers don't seem to be as important, and for all of this work, I've not included any of the galaxies that are at that time undergoing a merger. It's quite interesting to see that I also noticed that at z equals 0, the fraction of halos growing at lower halo mass is actually lower than the fraction of the central galaxies at the same mass, and that's obviously a reflection of the recycling that's happening. Yeah.
Okay, Emily says, interesting talk, Ruby. Do you have plans to see if the balance of inflow outflow is different at earlier times?
Yes, definitely. And this is all, will definitely all be included in the paper. I was gonna, the paper that I'm writing, I was going to include sort of GIFs of all of these different plots evolving over redshift, but I didn't want the computer to crash. I was a bit worried about it.
That's a fair worry. Right, so maybe just, we'll go to Sarah's. She says, it would be interesting to see how the centrals change with different halo masses as a fraction of growth versus stellar halo mass. Plot showed there is a dependence. So it's more of a comment about possibly looking at something.
Yeah, absolutely. I entirely agree. And it's something I want to look into. Yep.
Okay, so just the last question from Katie. She says, great talk. You showed that centrals with the highest M star to M200 ratios are not accreting gas to the ISM. Does this imply that some mechanism has stopped the accretion, since presumably there would have to be accretion at some point in the past to get a high M star to M200 ratio?
Yeah, absolutely. It's very true. And we're seeing that this sort of growth fraction at high redshift was higher. It was still the lowest of that full parameter range, where the centrals are more in a field environment. But it does sort of drop with redshift. And I assume it could be to do with cosmological expansion, right, where the surrounding density as we go to redshift 0 is a lot lower, and the likelihood of gas being attracted to a lower mass halo is also lower.
Okay, let's thank Ruby again for her great talk. And James, if you're online, can you?
I am online. Hi.
Okay, can you share your screen?
Sure. Give me a moment. Okay, that should be shared. Let me get into this presenter mode.
Yep, you might want to go to your first slide.
Yes, that's a good idea.
Yeah.
Yeah, okay. Here we
Okay.
go. Got
Yep.
it.
So James Leung is going to be talking to us about searches for gamma ray bursts afterglows with ASCAP.
That's right. Thanks, Christine. So I'm James, everyone. I'm going to be shifting gears a little bit And
Thank you for having me here today. My name is Julia, and I'm a third-year PhD student at the University of New South Wales, working with Sarah Braff. Today, I'm going to talk about my most recent PhD project, focused on reconstructing the internal mass distributions and the orbital structures of semi-massive galaxies
Hold on.
using spatial orbit superposition models. Now, before going into that, let me just give you.
all right, that
I
was
think they figured it out.
Okay.
Okay, go ahead,
Awesome.
James.
Okay, awesome, thanks. Yeah, so hi everyone, I'm James, and I'm going to be shifting gears a little bit with the whole ASCAP focus. And instead today I'll be talking to you about how we use ASCAP to find gamma ray burst afterglows. So to give a brief introduction on what gamma ray bursts are, they're essentially these extremely energetic cosmic explosions that happens along a beamed axis. And if Earth is located along that beamed axis, then the jet that's launched from this explosion will eventually produce a flash of gamma rays that's picked up by one of our gamma ray satellites, and that's what we call a gamma ray burst. And usually lasts for a couple of seconds up to a couple of minutes. When the jet expands outwards over here, it starts to interact with the external medium around it, and the jet will start to spread sideways. And as it starts to spread sideways, it gets a little bit less energetic, and it starts to produce an afterglow emission that can be observed at bigger viewing angles and at lower wavelengths, such as at the radio frequencies. And in fact, this radio emission that comes from this afterglow can be studied years after the initial gamma ray burst itself. And so today I'll be talking about how to actually find these radio afterglows using our ASCAP telescopes. And in particular, I'll be focusing on the two wide field surveys that we used. The Rapid ASCAP Continuum Survey, which covers the entire sky south of plus 40 or plus 30 degrees declination, and the Variables and Slow Transients Pilot 1 survey, which covers this red region over here. And that VAST survey has a cadence of about 2 to 3 months. So it's repeated once every 2 or 3 months, and has a total of about 5 full epochs. And both of these surveys get to a depth of around 250 to 300 microjaskies per beam, and it's at a central frequency of about 888 megahertz. So it might be odd to ask the question, for example, why would we want to be studying gamma ray objects in radio, and why use radio surveys to study these gamma ray bursts? So there's a few good reasons for doing this, and I'll go through some of them with you today. So the first reason is because radio afterglows are actually essential for helping us probe the energetics and microphysics of any GRB events. It's one of those things that help us really identify what the environment of the event is like and what the jet structure is like, and helps us to get a estimate of the energetics independent of the viewing angle. The second reason as to why we might want to be using these wide field radio surveys instead of just traditional follow-up methods where we point a telescope to a certain burst that we already know about, is because these wide field radio surveys allow us to give an unbiased follow-up of all the events that are in the survey footprint. So if you have some unexpected emission that comes years and years after an event that you wouldn't have really known about or predicted, then these wide field surveys would be able to pick it up. And these type of unexpected late time emission could be things related to supernova rebrightening, which is usually associated with some forms of gamma ray bursts, and so forth. And not only that, it allows you to sort of do a better population analysis on bursts that are detected in the footprint. And these are going to be very important in answering some of the open questions about gamma ray bursts, which include why, for example, some long gamma ray bursts are associated with supernovae, why some are not, and why do we see cocoons, or basically essentially ejecta, that's sort of choking the jet that's being launched in some bursts, and why they're not in other bursts. So it really goes towards the fundamental question of what really happens to these stars as they approach the end of their lives. And the third reason why we might want to be studying these gamma ray bursts with wide field radio telescopes surveys is to find these off-axis or orphan afterglow events. So if the burst looks something like this, and Earth is located here, then you won't see the initial flash of gamma rays that won't be detected by our gamma ray satellites. And the only way in which we can be knowing that such an event ever happened is to detect the afterglow emission that comes from that burst when the jet has expanded sideways to a larger viewing angle. And we could be probing for that off-axis afterglow using wide field radio surveys. And so that's very useful for us in estimating the true GRB rate and giving us some insights into the geometry of the jets. Okay, but one of the problems with these wide field radio surveys is that because of the wide nature, they usually don't go deep enough and sensitive enough to detect these radio afterglows, and as a result, it's actually quite tricky. So today I'll discuss a couple of ways in which we went about trying to investigate or find these radio afterglows. The first thing that you might expect to do is basically just take a list of well-localized GRB gamma ray bursts and cross-match it with a list of radio sources from the Rapid Eye Spectrum Survey and the VAST Pilot Survey and see if there are any matches. So it turns out that we had 4 matches, and one of the things that we need to figure out is whether or not the radio source that was matched is actually host related or afterglow related. Okay, so does it belong to the host galaxy or to the afterglow event? And it turns out that one effective way of doing this is to look at position offsets in optical images between potential host galaxies and GRBs. So I'll show that in the next slide. But the key takeaway from the slide is that from this type of search, we found one afterglow candidate, and this was this afterglow candidate belonged to GRB 171205A. So you can see in this pan-stars image over here, the host galaxy in the background, and the initial search basically found a match to radio source given by the blue contours, which is essentially the radio contours from the RACS observations. And what you're able to see here is that the fitted position of this radio source is given to you in white, and you can see that this fitted position is much closer to the GRB position, which is where the image is centered on, than it is to the host galaxy position. And from this, we suspected that this radio source could be from a GRB afterglow. And this was indeed confirmed in a compact array follow-up as shown by these red contours over here, which basically gave us confidence that the position is coincident with the afterglow event and not with the host. And so this is actually one of those really, really exceptional GRBs. It's a local GRB at this redshift 0.036. And it's a low luminosity GRB with a supernova component to it. And it's actually the 6th closest GRB that we've ever detected, the 4th longest studied GRB, and the 2nd brightest at gigahertz frequencies. And so you can imagine that it's been studied quite widely before, but actually, so the late time data points was actually very, very late time. So the detections that we made were more than 500 days after the burst. You can see all the other data that's out there on this burst was before 100 days. And there's been the X-ray observations probed for the prompt emission, and the optical and near-infrared observations probed for the supernova emission. And the key takeaway from this is that the early time X-ray and optical observations revealed to us that this GRB event seemed to have had signatures of this thermal cocoon type of signature that I was alluding to earlier. But what's not been studied is the afterglow emission from this event. And as I was discussing earlier, the radio provides a very good way to study the afterglow emission. And so if we look at the spectral energy distribution of the event and see how it evolves over time, and focus, for example, on just the radio, we can compare it to known standard afterglow models, and the evolution of the spectral energy distribution in this case, in particular, the turnover of the evolution of the self-absorption frequency towards lower frequencies is essentially a very strong indicator that this burst actually occurred in a wind-like environment where the density falls off as 1 over the distance squared. We're able to actually back out a lot of microphysics from the event just based off our radio observations.
James, you have 5 minutes.
Oh, awesome. Okay, thanks. And so one of the challenges that I was previously alluding to is that it's very difficult with wide field surveys, that the sensitivity is sometimes not enough to detect a lot of the fainter GRB events. As I was saying, this event was the second brightest at gigahertz frequencies. So if we want to be finding fainter events, what we might want to be doing is searching through deeper ASCAP fields. And essentially how we went about doing this was to do a CASDA search on all the different ASCAP fields that were on CASDA, which include EMU, Wallaby, GasCap, and so forth, and see if there are any matches to any radio sources in that field to GRB events. And one of the matches turned out to be associated with GRB 150428A in a Wallaby field. And essentially, this is sort of shown by this Wallaby radio source is shown by this green contour, these green contours over here. And you can see it overlaps with the GRB position centered on this image. And there was a reported host position for this gamma ray source, gamma ray burst source, which was given the sign crosshair over here. And so it seemed like it was offset from the host and probably gamma ray burst related. And so we did a follow-up of the source 2 years after the Wallaby observation, and with the GMRT and also the compact array. And we could see that with the follow-up, all the data points lie really nicely on this power law, which seems to indicate that there was no evidence of fading for the event. So it's more likely that the radio source that we saw was a host galaxy and not a gamma ray burst afterglow. But what's really interesting about the source is that this was a dark gamma ray burst. So this means that the burst was not detected in any optical wavelengths, and a reason for this could be because of dust suppression, dust obscuring the optical wavelengths, and so you're not able to study the burst nor the host galaxy in those wavelengths. And perhaps the radio emission from the host galaxy would be one way to study the host galaxy for this dark gamma ray burst. So I've only talked about the challenges of related sensitivity of the ASCAP surveys, but often when we're dealing with variables and transients, what we want to be doing is looking for transient or variable behavior in the temporal domain. And so generally how we do this is putting together a plot like this, the eta and v plot. And this is essentially showing the degree. Yeah.
You have 2 minutes.
Yeah, that's fine. This is essentially showing the degree of variability against the significance of variability. And we identify variables and transients by looking at the top part of this phase diagram, okay? According to some threshold. But because these gamma ray bursts are very slowly varying, they're actually in the middle of the pack over here, and it's actually a huge challenge to find these afterglows using traditional variables and transients searching techniques. And so the way forward is actually to get more information about these bursts, and that means coordinating with optical surveys, and as well as trying to do some template matching to find bursts that only decay with a power law and shows no oscillatory type of behavior. So hopefully I've shown some of the challenges that we're facing right now in terms of searching for gamma ray burst afterglows. Right now, we're only probing the very, very local and bright GRB afterglow sources. And we'll take some clever techniques to push down below this threshold. And there's still a lot of this phase diagram to be explored. So thank you, and I'm happy to take any questions.
Unfortunately, we don't actually have time for questions, but James, there are a couple in the Slack channel. If you could answer those offline.
I'll get around to that. All right,
Yep,
thanks.
thank you. Can we thank James again? Okay, great. So we have another talk here at Curtin, and it's by Kariuki Chege, who will be talking about ionospheric effects for the MWA epoch of ionization project.
Hi everyone, my name is Kariuki Chege and I'm a PhD student at Curtin University and I'm with the MWA EOR group. My work is on the ionosphere and its effects on the EOR observations, and that's what I'll be talking about today. So to begin with, here I'll try to summarize the introduction into the EOR and the observations we do with MWA. And we start with the Big Bang, where the universe at first is fully ionized, and then as it expands and cools, it gets cool enough for neutral hydrogen to form, that is atoms of neutral hydrogen forming due to the combination of protons and electrons. Now, as the universe expands, gravity causes the very first stars to form, and these stars emit radiation that starts reionizing again the neutral hydrogen. So what we are trying to observe is the 21 centimeter signal emitted at 1420 megahertz by these neutral hydrogen when the spin flip changes. And due to redshift, these emission can be observed now at much lower frequencies, which is what we try to observe with the MWA. And these lower frequencies are also not a very good thing, because at low frequencies, a lot of bad things starts happening. And some of them are the RFI, because at these frequencies, it's where for example, the FM stations transmit at. And also, for some reason, sources start getting weirdly much brighter, and that's a problem for us. And unfortunately, we are also sure that at our current sensitivities, we cannot detect directly these 21 centimeter emission using our current instruments. And for that reason, we are now trying to pursue a statistical detection of the signal. And on the right here, I'm showing a two-dimensional power spectrum of the 21 centimeter emission. Fortunately, a radio interferometer, it's like a natural power spectrum machine. So we can easily obtain a 3D power spectrum of the sky we are observing. And then we can average over a lot of data, improving our signal to noise ratio, and then collapsing it into such 2D power spectra and also 1D power spectra, where we try to get the limits and see how well we're doing in trying to detect the signal. Now, you notice the region denoted as the EOR window, which is where we expect that the 21 centimeter signal will be dominating, and that's where we have the best chance of detecting it. And the wedge is where like all the bad stuff belongs. And we are this close to detecting the signal. And by this close here, I mean maybe a couple order of magnitudes away. So work is still going on, and the MWA has been at the forefront of pushing these limits down. And with the latest results from Trott et al. 2020 and a couple of submitted papers by Yoshura and Rahim et al., 2021, which also are improving on these limits. So why is this signal so elusive? First, as I mentioned, it's very faint because it's way back in time, and then we have way much brighter stuff in the foreground. So these foregrounds are what we need to eliminate, and that's easier said than done, because before we can accurately get rid of these foregrounds, we need to solve a whole host of problems that come with our instrument, and also the way we calibrate the data that we observe with it. So the first problem is the beam, and on the right here, I'm showing an MWA beam response at 150 megahertz for a zenith pointing on top and a 30-degree pointing at the bottom. And you can see that it's not a very good scene to work with, especially with all those big nulls over there. And that's not the only problem. We also need to solve its polarization leakage. And on top of that, you need to have very accurate sky models, very accurate sky models. And as I say, at lower frequencies, bad things happen. The ionosphere is actually very violent at these frequencies. Now, my work is mostly about the ionosphere. And the ionosphere is a collection of ionized plasma at hundreds of kilometers, around 200 onwards above the Earth's surface. And it has a lambda squared relationship with frequencies. So that means that at lower frequencies, it's very turbulent. And for the MWA, which actually has relatively short baselines, and it's not very large physically, the ionosphere becomes a direction-dependent problem. And this means that sources shift in position as you're observing them. So it's like just sources moving and dancing around in the sky. And we try to model these using a thin phase screen. So this is what I tried for my PhD. And because we can look at every line of sight toward each of the sources in our sky model, and then we can try to calculate the phase difference that we should see based on the given ionospheric screen that it's available during that observation. And this setup is shown on the bottom left, and on the right, I'm sort of showing a typical source shifting and also some slight deformation on it. And I applied this setup to come up with a tool that can be used to simulate these visibilities that are contaminated by different forms of ionospheric content by the ionosphere. And the reason why I had to do this is because we need to first simulate these effects as well as we can, and then we can understand the effects on our power spectrum. So how this works is the user can just input any kind of ionospheric phase screen depending on its the level of turbulence and the structure in the ionosphere, and then using the configuration of the array, we get all the PS points towards all the sources in the sky model, and then we can include the beam and all the other like noise parameters about the instrument, and then get the contaminated visibilities. And in this plot here, I'm showing some of the simulations using this tool, and we get on the left a simulation of increasingly bad ionosphere, and we should expect the longest baselines, which are most sensitive to the smallest scales, to be the worst affected. And this is what we see from the gains, from the various of the gains phases. And on the right, we can see the lambda squared relation, where lower frequencies get more source shifts, more larger source shifts, and that's what should be expected. And now that we have those simulations, we can try to use them, and propagate those simulated visibilities through our UR pipeline, and also try to relate them to real observed ionospheric situations at the MRO. And this has been characterized before by Jordan et al. 2017, where they found like 4 dominant types of ionospheres MRO based on the magnitude of those offsets and also the sort of the isotropicity on the structures that can be reconstructed from these phase shifts. Now, the question I'm trying to answer is how exactly do these shifts or these 4 types of the ionosphere affect the power spectrum, and also how can we improve on these effects? And here I'm showing the one-dimensional power spectrum for a suite of simulations with different ionospheric conditions. And I'm also trying to improve on the calibration that is usually done in both the direction-dependent calibration and also the direction-independent part of the calibration pipeline. So what we see here is that on the bottom 3 plots, where we have, so each line here represents a single observation, and each color is also a different calibration parameter. In this case, a different number of calibrator sources. And the bottom 3 plots show the worst ionospheric cases that were simulated. And this is just what we don't want to happen, because our calibration doesn't work anymore, and we cannot differentiate even between the different calibration parameters. On the top panel, we can see that the green solid line at the bottom is where we get the best, the least contamination in our power spectrum. And this is when we use the most amount of calibrator sources in our model, which is something that was not happening before, maybe because of computation problems. And we can also look at the effect of these on the 2D power spectrum, where downwards I'm increasing the intensity of the ionosphere, and then on the left I'm using more calibrators. And before, the third column is what the calibration pipeline has been used, and this is what has been used to publish the most recent limits. And we see that we can start to push this more, especially when the ionosphere is not extremely bad, to places where we have even less contamination in the EOR window. Now, I moved on into looking at real data, and here I have processed around 10 hours of real MWA data and checking how bad the ionosphere can get. So on the left, I've included all the 10 hours with all kinds of ionospheric activity. And we can see that indeed there is contamination even in the window itself from the ionosphere, because when we remove half of the worst data, we actually get much better limits from that. And on top of that, when we use the updated calibration parameters, we get even better power. And this is what happens to most of the surveys when doing the EOR, where almost half of the data is not used because the ionosphere is actually bad, really bad, and it's just making the limits worse. And to try and find a possible solution to that, I looked at the different ionospheres, and we see that there are 2 types of ionospheres that have the least power. And when I looked at the window, we find that one of these was found to be, was recently thought to be very active, quite active, but in the window we find that it has even lower power at certain modes. And these give the possibility of using some certain active data based on the spatial structure of the ionosphere in predicting our limits, so which is a good thing. And that was my last slide. So to summarize, I've come up with a tool that sort of helps us simulate different ionospheric conditions. And now it's showing that we can use slightly active data, choosing different specific modes of it where the contamination is least to try and improve on our limits, because we need as much data as possible. And the next step is using these together with a lot of other improvement that is happening in different aspects of the instrument, as I mentioned, the beam, sky models, and so on, to try and get even better, push those limits lower. Thank you.
All right, thanks, Kariuki. So maybe as we switch speakers, you can answer this question from Mike, who asks, for your 1D and 2D plots, you mostly increase the directional independent calibrators. Did you also look at what happens when you increase the number of direction dependent calibrators?
Yes, so at first, yeah, so here I'm actually increasing both of them. At first, I wanted to just check mostly the direction dependent one because the ionospheric problem is direction dependent, but also it turns out even that increasing the direction independent one also has an effect. So actually increasing both helps.
Okay, so there is, looks like there's gonna be another question from Nicole here, but maybe you can answer that on the Slack so we can move on. So let's thank Kariuki again. And Chris, if you're there, can you share your screen?
Yes, I can. Okay. Let's go there and
Yep, that looks good. Okay, so for the last talk of the session, we have Chris Riseley. Oops. Who will be talking about unpacking the complex merger in Abel 3266 with ASCAP EMU and the compact array.
yes, indeed. Thank you, Christine. Yes. Hello, Australia, Italy calling. I'm dead excited to be able to join you virtually. Wish I could be there in person, but you know, things are difficult at the moment. I'm dead excited to be talking to you today about this project that I'm leading, working on this particularly beautiful and complex cluster merger that you can see in the background here. I'd just like to give a quick shout out before I go too far to all of the people that I have been working with on this. And there are a smattering of names there in the lower right-hand corner of the screen, who are people who have contributed directly with data or analysis or verification or doing some observing. So a bit of background first, just to go through this briefly. Clusters are awesome. They're great physical laboratories. If you're interested in a variety of astrophysical processes, you can learn about them by studying clusters. In terms of diffuse radio sources, you get these things like radio relics, which you can see here on the screen. They're these extended filamentary arc-like sources that tend to sit at the cluster outskirts. They are linked with merger shocks. So if shock physics is something you're interested in, you can learn a lot by looking at clusters, by studying radio relics. And the leading theory is this diffusive shock acceleration mechanism, which, you know, I could spend a whole talk talking about that, but I won't. If you're interested in turbulence, then you should also study clusters, because clusters are full of turbulence, where you get these mergers. Turbulence is dumped into the ICM and can spin up these large-scale radio halos, which are these kind of amorphous, blobby, unpolarized sources that tend to follow the X-ray surface brightness. And yeah, they're thought to be spun up by energy dumped from the merger into the intercluster medium. And finally, here's some pretty simulations from Franco Vatsa. In cluster environments, you also get a wide variety of bent tail radio galaxies, which is just a catch-all term for all these wide angle, narrow angle, head tail, etc. radio galaxies. And they hint at highly complex evolutionary history and complex interactions. And you can see here in this video that we'll keep on a loop, simulated radio contours and X-ray surface brightness in the color scale. And as you can see, as the subclusters fall in, you get lots of interesting radio morphology. And here are some pretty examples. On the left is a paper by Amanda Wilbur from a couple of years ago, looking at some LOFAR data. And in the center there is a fantastic, spectacular, highly complex radio galaxy in a poor environment that is coming soon to nature astronomy. So clusters teach us a whole bunch of stuff about magnetic fields, particle acceleration mechanisms, interaction between thermal and non-thermal stuff, dark matter, galaxy evolution in these dense environments. Basically, clusters teach us all kinds of stuff, and they're really cool. They also make pretty pictures, as I'm about to show you. So here is a beautiful map of ABL3266, which is this cluster that I've been working with for a little while now. In the background, you can see an image from the Dark Energy Survey with cyan, little cyan circles that hopefully you can pick out, identifying cluster member galaxies. I'm pretty sure that I've said this every time I've given a talk at the ASA, so at the risk of sounding like a scratched record, this is probably the coolest figure I've made in my academic career so far. What we have in terms of overlays, in blue, you see X-ray data from XLM Newton in the blue channel. This traces the hot plasma. This is Bremsstrahlung emission. So this is the thermal component of the intercluster medium. And you've got radio data overlaid in the red channel. You've got ASCAP at 943 megahertz, data from early science with EMU. And in the green channel, you get 2 gigahertz compact array data. So all of this radio emission traces cosmic ray electrons and magnetic fields in the ICM. So that's your non-thermal stuff. As well as being a pretty picture, this also can teach us some science. So how do you interpret an image like this? Stuff that appears yellow is your kind of typical steep spectrum active galaxy. So your kind of spectral index of about -0.8 to -1. Stuff that is red, and the redder it is, the steeper the spectrum is. Red is ultra steep spectrum emission, so very steep spectral index. This traces old, aged plasma. And finally, there are some, anything that appears green, and there are a handful of green appearing radio sources in there. That's actually inverted spectrum, which tells us that there's some interesting physics at play. Maybe there's some restart activity going on, maybe there's some self-absorption at low frequencies. There are many sources of interest, which I'm going to attempt to unpack in my remaining time, but I'm going to talk about the wrong way relic, which is this thing to the south, this fossil remnant up to the north, and this complex remnant here that you see worming its way through the rest of the cluster. There's many other things I could talk about, such as all of these sources, but I don't have the time to, so I've just picked the 3 shown here in green. First up, let's jump into the wrong way relic. It's got an arc-like morphology, it's got a linear size of about 0.5 megaparsec, and it's located in the cluster outskirts. It's got a very steep spectrum, as you can kind of infer here from the maps, showing ASCAP on top at 900 megahertz and compact array at 2 gigahertz on the bottom. And it's also co-located with an X-ray shock. Now, we call it the wrong way. It's been dubbed a wrong way relic because the curvature is kind of the opposite way to what you'd expect from a shock going from the north to the south. However, simulations can give us an answer to this. So what you see here is some simulations of a cluster merger with X-ray emission in a color scale and radio emission in contours. You get your turbulence and your shocks in the left panel that start to generate this radio emission. Then by the center panel, this sort of textbook arc-like relic has formed. And then by the time you get to the right-hand panel, the subcluster that's merging from the right has dented in the center of that outward going shock and disrupted that really nice arc-like shape. So you get this inverse curvature. So actually, these are relatively straightforward to generate in simulations. You can look at Mach numbers, which basically traces the strength of the shock independently from radio, from our radio data, and from X-ray data from the recent Eurozeta paper. We actually find very consistent Mach numbers, which is fantastic. This implies that the relic is steamed quite edge-on, so we expect a lot of polarized emission. This is a weak shock, and there's only a fairly small handful of clusters with shocks detected clearly in both radio and X-ray. And if you run the math, which again I could spend a whole talk going into, diffusive shock acceleration cannot boost your thermal electrons to generate this kind of relic. You need a pre-existing, mildly relativistic fossil population. So this is really cool. We're learning some more about DSA physics and reacceleration from this relic. Moving on to the fossil remnant, this thing is extremely cool. It's got this diffuse complex morphology, which strongly suggests that it's part of the cluster. We wouldn't expect something with this morphology to sit outside a cluster. Despite our extremely sensitive 2 gigahertz data, we don't see any sign of this source at all with the compact array. So this implies the spectral index is less than -4.9, which is close to the steepest spectral index ever measured. There's many ways to try and select remnants. Before I go any further, I should mention that what we think is happening here is we think the host galaxy is this thing at the southeast tip, which is at redshift 0.0559. That is a cluster member galaxy, so it's kind of on our money. You can see this source, which kind of lands up nicely in the middle, but in the beautiful Jez data, you can see diffraction spikes, which means this is a foreground star. This is not a galaxy, so it cannot possibly host this source. The index is extremely steep. We get the fantastic coverage from Gleam, which has an in-band spectral index of about -1.3. There's a bit of wibble in there. But above about 200 megahertz, it breaks sharply and goes down to a spectral index of nearly -3. However, you may notice the open triangles. Those are actually upper limits from some Cat7 data that I looked at during my thesis. So what this really means is that actually this spectrum is probably curved and much steeper than implied here just by the broken parallel fit. We'll need things like SKA low and the phase 3 MWA at 300 megahertz to look at this more. You can look at remnants, and people like Marissa Brienza and Ben Puichi have done some really awesome work on selecting remnant radio galaxies. We don't see a core, so this is probably a remnant, although what's called the core prominence, which is essentially a measure of how much flux you get from the core to how much flux you get from the overall object minus the core. This core prominence is actually kind of high. So for remnants, typically you expect a core prominence of less than 10 to the minus 4. But this is mainly based on the sensitivity of the SCAP data and the extremely ultra steep spectrum. So really, I'm guessing that's a 5-minute warning, Christene?
Yeah.
Fantastic. So based on the morphology, the ultra steep spectral index, and this spectral break implying the curvature, this really has to be a fossil AGM remnant. So this is going to be really cool to study once we get into the SKA low era and we start to get this kind of really high resolution that we need. Finally, this complex relic, this complex remnant rather, it's not a relic. It's spectacular, it's beautiful, it's got this really interesting nitty-gritty, knotty morphology. One of the questions that's been playing around in my mind, and the minds of my colleagues who've been working on this, is this a single source? Is this multiple remnants? Well, what we think is that the host galaxy is this galaxy you can see here at the very tip of it. That would give this a largest linear size of about 0.5 megaparsec. So this is quite extended. But we see here's an image that I showed you earlier, just flip reverse, and we see similar kind of morphologies for known radio galaxies in other clusters. So these things are not, this kind of complex morphology is not unprecedented. It's also got a very strong spectral index gradient, which supports the remnant scenario, going from a kind of -0.8, which is fairly active near the host, down to steeper than -2.5 all the way down in the tail, which is it's again further evidence that this is remnant. We don't detect any kind of radio core, which actually allows us to put very stringent limits on the core prominence. So 10 to the -3 to 10 to the -4. This is definitely a remnant. But then the question is, why does it have this clumpy, irregular morphology, and what are these faint threads? Well, we can turn to X-ray data here, and what I'm showing here is an unsharp masked image from X-Men Newton. Basically, what you do is you take the X-ray surface brightness and you convolve it with 2 different Gaussians and you subtract them, and it gives you a spatial filtered image that allows you to look for substructures. And we see some edges here, which are helpfully indicated by these arrows, and I've roughly sketched on the line there. So what these edges trace is an old historic passing shock that has likely gone through and disrupted and revived this remnant somewhat. So that's generally what we think leads to this complex morphology, basically an inhomogeneous reacceleration. I would also note that edges are seen in this region by Erosita as well. So, this goes to show that our independent analyses are pretty much strongly supported by all the various different evidence. Wrapping up, I'll show this image again because it's lovely. I love it. It's amazing. Able 3266 is this highly complex system. rich substructure. You've got 2 main subclusters and 6 subgroups, all merging in this complex environment. We've got a plethora of fossil radio galaxies and bent tails. We've got a new radio relic, which is conclusively shown to be generated by shock reacceleration. There's tons more to come. We've got many active galaxies, other remnants, other diffuse radio sources, and we've got complex array data, so it's full polarization. So I'll be able to reconstruct the magnetic field structure in 3D, which is going to be really awesome. And yeah, I'll stop there and take questions. Thank you.
Thanks, Chris. That's a really great talk. So there's a few questions here in the Slack. The first one's from Luca. They say, very nice data. Regarding the fossil remnant and the complex remnants, do your data allow to obtain a rough estimate of their age?
Oh, that's a really good question. The fossil remnant, so this one up to the extreme northwest. Yes, we can probably reconstruct that from the spectral break frequency. Just waiting on an analysis of the phase 2 NWA data, which gives us much better resolution, so that we can disentangle the blobs that are seen in Gleam to do that more properly. The complex remnant, it gets a bit more tricky because we've only got 2 frequencies at the moment. Really, if we want to look for curvature and spectral breaks and that kind of thing, we probably need some higher frequency data. I would love to study this cluster with the 4 centimeter band using the compact array, but to survey an area of this size to this sensitivity, we're going to be talking hundreds of hours. So that is a future project, future large project.
Yeah, that sounds like some pretty intense work there. So the session's gone a little long, but there are a few other questions in the Slack, Chris, if you could answer those offline. But
Absolutely.
let's thank all of the speakers for the session. That was a great session. And then a reminder that during this break, there is an industry engagement session using Zoom 3, if you want to attend that.